Okay, we're moving into chapter 7. Now, in chapter 6, we talked about the normal probability distribution and the standard probability distribution, and we started looking at, situations where we know things about the population mean, population standard deviation, and we're going, okay, let's say I get a value. What's the chance that value would be, you know, this far over on one side of the distribution, or that side of the distribution, or in the middle somewhere? What are those probabilities? And one thing that may have kind of crossed some of your minds was, well, most of the time we're not going to know things about the population mean. I mean, that's why you're doing studies. That's why you're taking samples, is to kind of get some idea about the population mean. So why did we spend so much time on that if we don't really know that most of the time? Well, for a couple reasons. The first reason is sometimes you do know. Sometimes you know from just research, studies you've done in the past. You've studied so many things, samples, so many people, whatever. I'm thinking about like that blood test. We did a problem about white blood cell counts or something, and you just think about like how many tests have been done on people throughout the years, and they have enough data that they can say, you know we are pretty confident this is, we're at a very high level of confidence that this is what the mean is, and this is what the distribution should look like in a healthy person. Now, not everybody's the same, so there is some variance, but usually that variance is within a very small margin, one way or the other. And so they're usually, I mean, you think about like human body temperature. You know, we have the official human body temperature, but for example, you're not really thought of as having a fever whenever you're higher than that. It's when you get to like over 100 degrees or 101, that's when you're considered to have a fever, because there is some variance in between there. But it's when you get so far to one side statistically, so far to one side, it may not seem like, you know 2 or 3 degrees is really far, but in a statistical measure, it gets you out there, because of the standard deviation, how far normal fluctuation would be. um, you get We can make some predictions about this. So that's one reason. Another reason is more fundamental, is when you're studying things, a lot of times it's easier to start from a situation like, let's say we knew what was really happening, and then we can develop some rules from there. And then once we have those rules, we can use those rules to go back the other way. And so when we have samples, then we can do that. And that's kind of where this is going. This chapter is going where, now that we know things about, what if we did know the population, what if we didn't know about things about the population, and we took samples, could we make predictions about the actual population? And that's where this is going here. We're going to be estimating things like the population mean in this section, in this chapter. So this is where, that's just all background, just kind of getting us started on this. So what we're going to do is we're going to have a sample. We're going to measure its mean, and we're going to say, okay, we're going to use this as an estimate for the population mean. Now, obviously, some ideas of like, is it a big enough sample? Is it truly random? Whatever. But we're not going to say it's perfect. We're going to go into the problem understanding this number we got is probably not the actual mean, but it's an estimate, and we're going to use it as kind of to be around the actual mean. Okay, so that's kind of where we're going here. And what we're going to do is we're going to ask ourselves, how confident do we want to be about this as a point estimator for the population mean? How confident do we want to be? Like, let's say I want to know what portion of Americans prefer Coca-Cola as a beverage. If I said, I want to be 100% sure I know what the right value is, then I would say, okay, I can be 100% sure. This is how I'd be 100% sure. It's somewhere between 0 and 100. It's somewhere between 0% and 100%. That it's somewhere in there. I'm 100% confident it's somewhere in between 0 and 100%. Well, obviously, you're probably not going to be, that's not going to do you much good. So then you want to start narrowing that down, and you start going, okay, maybe I'm okay being 90% sure. Well, then that might drop it down to, well, it's somewhere in, somewhere between 45 and 55% or something, whatever the percentage. I don't have any idea what the percentage actually is, but it's somewhat. Now we can start narrowing it. Now, understand how that's going to work. We're gonna the higher the confidence, the higher the confidence, the bigger the interval we're going to cover. Okay. The lower the confidence, the smaller the interval. So if you want like say, I don't want it to be between 45 and 55. I want it to be between, like not 10% width. I want it to be, maybe it's only, 5% width. Well, now I'm going to be less confident about that measurement, because now since I'm narrowing it down, smaller interval, my confidence level has to be smaller. So you're going to see this kind of dichotomy there, that if the more confident you want to be, the bigger you have to make the area to cover, that value somewhere in there, the real value somewhere in there. So, it's like, I want to be more sure, you have to be less precise. If that makes sense. So to be more accurate, you have to be less precise. In this case, we will actually get a range of values. So this is what I'm talking about, this interval, and the size will be based on the confidence level. And as we get more confident, this interval is going to be wider. As we get less confident, this interval is going to be smaller. Okay. So some assumptions about this random variable X that we're looking at. So the size n, simple random sample. So we're going to do a simple random sample, get a size n, is going to be drawn from this population of X values. Okay. We're going to assume we know the actual population standard deviation. Okay. So again, we're back in that situation. Like, how do we actually know something about the population? We're doing studies. Again, those same reasons I talked about before. Maybe we've done other research, and that's why we have this idea that we know what the population standard deviation, even if we're not sure about the mean, maybe the mean's changed, we still think the standard deviation may be the same. Because remember, mean and standard deviation are not tied to one another. They're both tied to the distribution, though. So, and just to make the problem simpler, but don't worry, we're going to look at problems in the future where we don't know the population standard deviation. But right now, we're still in that assumption phase. We still know the population standard deviation. All right. If the distribution is normal, that we're drawing these things from to do our sample, if we know that's normal, then any size is going to work. We can use any size sample. If it's not normal, though, we're going to want to pick samples bigger, 30 or bigger. And ideally, we would pick things, even more large than just 30. We would, push it up to at least 50 or 100. Again, the larger your sample size, the better the estimate's going to be. The better the estimate. So we're going to have some things kind of like, if the confidence goes up, then the interval is going to go up, right? To be more confident, I have to make it bigger. But if the sample size goes up, the interval is actually going to get smaller. The interval is actually going to get smaller because I'm going to be more accurate. So I can increase my accuracy. I'm going to be more precise. I should do it that way. I can be more precise the larger the sample is. To be more accurate, to have a higher confidence level, I have to have a larger interval. Okay, so these things are kind of acting against each other. And you're going to want to optimize these, I want to be confident, but I also want to, so I want to be accurate. I want to have a high confidence level, so I want to be accurate, but I also want to be precise. So I need a large sample size. That would be the ideal situation to kind of go here. All right. And what we're going to do is we're going to find the margin of error. So you probably have seen places where it said so many American, they'll say something like 60% of Americans think blah, whatever. And then at the bottom, it'll say, the margin of error plus or minus, 5% or something. And that's what we're getting into here. This is this margin of error that they're talking about. So what that means is when they say 60%, they mean it's actually somewhere in the range of 55 to 65. It's somewhere in that interval. It might be 57, it might be 63. They're just saying we did a study, we got 60, we had this level of confidence, and we created this margin of error here that created this margin of error in this range around that. So we're going to call it 60 because that's the value we got, but we understand that it might be either way, up to 5% either way. So we're going to create a margin of error here for these intervals, and we're going to say that margin of error is defined to be the absolute value of our sample mean minus our actual population mean. That difference there is what we call the margin of error. So confidence level C is the percentage we want to be confident that the mean actually falls within that range. So we're going to, and very typical 95% confidence level is pretty typical. 90% is also pretty typical. 99% sometimes. But again, the higher the percent, the wider the interval has to be. The wider. Usually if they say most or, typically or something, they're talking about 95%. That's the most common one. All right. And what we're going to do is we're going to calculate a critical value, a Z value, based on this critical or this confidence level. So here's a list of some of the, well, I guess on the next slide, there is a list of some common confidence, critical values that we're going to look at. So we're going to say somewhere between the probability that our actual value falls in this set of critical values is going to be that confidence. It's going to be a 0.95 probability it's going to fall in that range or whatever confidence level we have. So this says for a confidence level of 50%, so 0.50, then the Z value would be 0.67. So that's when you have 50% in the middle. Okay, so you look on your table there and you would say, okay, what's the probability? Like 25% is below, right? If there's 50% in the middle, there's 50% on the outside. So 25% below and 25% above. And if you look at this for 0.67 or negative 0.67, let's say, you're going to see that's the closest to that 25% below. So 50% in the middle is how that would work out. All right. Okay, so here are some common critical values that you're going to see. And again, this is on page 362 in your book. It's also, if you look at that table I gave you, with this Z table, if you look down here, it also has those down at the bottom there. Are they all there? Let's see. 70, 75, 80, 85, 90, 95, 98, 90. Yeah, yep. So they're all there on that bottom of that table. So check that out. Has all these Z values. And you'll see things like 95% is 1.98. If you think about the empirical rule, we said 20 within 2 standard deviation, there was 95%. So this is a little bit more precise than what we used in the empirical rule. But it's close. I mean, you can kind of see where they got those values from. All right, so error tolerance. The error tolerance is the maximum margin of error. So the margin of error is actually exactly how far your sample mean is from the population mean. Okay, that's the actual margin of error. The error tolerance is how wide we're going to make that interval. this way or that way, plus or minus, so I guess I was a little imprecise when I said here, when I was talking about a survey margin of error. That should actually be the error tolerance. That's not the margin of error. That should be the error tolerance. So I'm sorry, I said that wrong. But the error tolerance is how far out you can go with that certain level. All right, and this is how you calculate the error tolerance. Is you say, I want to have a critical value, that Z value based on how confident I want to be, times the standard deviation divided by the square root of the sample size. And that's going to tell me how big that margin of error is. Now, there will be times, okay, well, here, let me say this. Confidence interval for this, when we know the standard deviation, it's going to be this margin, X minus the margin of error, and X bar plus the margin of error. So, or sorry, I keep saying margin of error. Error tolerance, I'm sorry. So you take your sample mean minus the error tolerance, you take your sample mean plus the error tolerance, and that gives you that interval. And you're like, the mean is somewhere in that interval, according to this level of confidence. I'm this confident the mean is somewhere in that interval. And then it's just doing a substitution. A lot of times, again, just like before, you'll want to calculate this error tolerance, and then you can just plug it in here. And probably several of the problems will ask you to calculate it individually, and then they'll ask you a question to go ahead and figure it out. All right, so let's look at page 371, number 16. We're going to create one of these intervals as an estimate, as a point estimator for our mean. So number 16. Okay, so uric acid in the body. All right, breakdown, over a period of months, an adult patient has 8 blood tests. So N equals 8, great. The mean concentration, so we got our sample mean, 535. And we have, we know the distribution of a healthy adult male is this standard deviation. So again, that's from countless studies they've done. They know it comes out to be that. So A, find a 95% confidence interval for a population mean concentration of uric acid in this patient's blood. What is the margin of error? So we're going to find the margin of error first. Or see, now that they're calling the margin of error. We're going to find the maximum error. Oh, that's the wrong thing. Look at that. Okay, so we want our confidence level to be 95. So C to be 0.95, right? So we're going to go to our table and we're going to say, what's a Z value that corresponds to 0.95? And that is a Z value of 1.96. That's a Z value of 1.96. All right, so we're going to calculate our error margin or error tolerance. And we said that is, I'm going to call this C because it's based on the confidence. Standard deviation divided by the square root of our sample size. So it's going to be 1.96 times our standard deviation of 1.85 over our square root of our sample size N. Now notice this sample size is smaller than 30. Is that okay? Well, yes, we're assuming we're drawing from a normal distribution that they probably say in here specifically. Maybe they do. Okay, I'm not seeing it, but I think we can safely assume this is. Oh, it's going to come into B. It's going to come into B. So we'll hold off on that for a second. All right. 1.96 times 1.85 divided by the square root of 8. And that gives us a E value of 1.28. And what we're going to do is we're going to create our interval here. And we're going to say, well, the mean has to be between somewhere in this interval. It's got to be the mean minus this error and then the mean plus that error amount. So it's going to be 5.35 minus 1.28. and it's going to be 5.35 plus 1.28. So 5.35 minus 1.28. So the actual value is, the actual mean value is somewhere between these two values. Somewhere in that value. So this patient's actual blood, or sorry, uric acid level is somewhere in that area, somewhere in there. We're 95% confident that it's somewhere in there. That's pretty confident. Okay. B, what conditions are necessary for your calculation? So okay. I'm looking at 17. Sorry, I was looking at 17 there. What conditions are necessary for your calculation? And that the distribution is normal. That has to be true because our sample size is below 30. Is normal. And the standard deviation is no. You know, if that's not really the standard deviation, if we're using the wrong value, we can't be that confident in that. So those two conditions have to be true. All right. So your results in the context of this, interpret this. Okay. So the question is, what's we doing here? Oh, just I think they just wanted us to say 95% confident that the patient's uric acid level is in that interval, right? I'm not going to rewrite it, but it's in that interval. All right, that's what how they want us to interpret it. Okay, sample size. Find the sample size necessary for a 95% confidence interval with a maximum margin of error. So I think we're going to hold off on that just now. For now, we're gonna wait for that. What I want to do is I want you to do 11, 13, and 21, and then we'll talk about how to find that D part. So 11, 13, and 21. Let me just real quickly make sure they don't have confidence, check the requirement, and the other one was 21. Yep, just work on those, and then we'll come back and we'll do D. All right, so pause the video, do those 3 problems, then come back. Okay, so moving on. All right, so here we go to D. To find the minimum sample size for a given confidence level and a maximum margin of error. So now we want to say, okay, I want to limit you on how wide you can take this interval. I'm going to limit that. But I'm also going to tell you how confident I am. Well, with those 2 bits of information, I can say, and as long as I know the standard deviation of the population, I can say, all right, I'll tell you how big the sample size has to be to make it work. It's got to be at least this big. And so this is just using some manipulation of algebraic manipulation of that equation. And you can get a formula that looks like this. You take the confidence, the Z value based on the confidence level times the population standard deviation, divide it by this maximum margin of error, this maximum error tolerance, and then you square that whole thing. Because if you think about like what the actual, what's the E formula? That was this, right? ZC standard deviation over the square root of n. So You can just do some algebraic manipulations, swap these around, multiply both sides by that, divide both sides by that, and then square to get rid of the square root. And there you go. That's a formula for how to calculate how big the sample needs to be. So now, what if this doesn't come out to be a whole number? Well, you got to round it up, and you can't round it down. It doesn't matter what it is. If it comes out to be 44.1, you got to say it's got to be 45, because 44 won't do the job. You got to push it up to 45. So you're always going to round it up. You're always going to round it up. Now, if it comes out to be 44, 44 is good enough, but probably it's not going to come out to be a whole number. All right, so now let's go back and do that D. So again, let's just kind of remind ourselves that's the formula. All right, so the sample size has to be our confidence level, our standard deviation, divided by our maximum error allowed, and then we're going to square that whole thing. So remember, our ZC, it's not 0.95, it's the Z value. It's from the Z value. So for a 95% confidence level, that's 1.96. Like I said, you're going to see 95 a lot. So 1.96 is going to come up a lot for this. Multiply that by our standard deviation, which is 1.85, and divide it by our maximum error we're going to allow one way or another. So we're going to square that. So 1.96 times 1.85. Divide that by 1.1, and that whole answer we're going to square. So I got 10.866, other numbers. This has got to go to 11, a sample size of 11. Got to take it to 11. For those of you who know that reference, turn it up to 11. So you got to push it up. You got to push it up there. Okay. So now I want you to do 15 and 17 as well. 15 and 17. And is that the end? Yep. All right. So, and then we're done. So have a good day. We'll have a quiz over sections 7.1 and 7.2. So watch for the next video there.